Hi, my name is Connor Bush. For this assignment, we are going to do a three-part derivation. We're going to start with this first part by deriving the basic equation of statics for an ideal gas. So first we're going to look at just one unit here. We'll label this point down here at altitude z. The top and bottom, the cross sections, will have an area A. This height here we will call height dz. So that means this point out here is dz plus z. So on just this basic cubic unit, there's going to be a pressure downwards. So we'll call this P, pressure at dz plus z. There's going to be the force of gravity down, so we'll call that mg. And then there's going to be the pressure going up at point z, so we'll call that z. We can do a net force equation, so the sum of the forces equals ma. We're going to consider that the acceleration is 0. For this situation, that's saying that this body is either moving at constant velocity or not moving at all. So if you can recall that a force is pressure over an area, so pressure equals force over area, so force equals pressure times area. So I'm going to call downwards negative. So we have negative P dz plus z times a minus mg. Get rid of this. And then plus the force down here. So that's P z times a, and this all equals 0. We're going to substitute the m term for mass. So we know that density equals mass over volume. So we can say that mass equals density times volume. We also know that volume equals the cross-sectional area times the height dz. So we'll call our mass density times area times dz. So we can substitute that in here. We're going to collect the pressure values together. I'm going to pull out a negative so that we have the difference of the top minus the bottom pressures. So P dz plus c minus pz. And then we'll just have that equal to density times area times g dz. And notice that the area terms cancel. So essentially right here, this is a difference in pressures, so we can just call this dp. And then we can divide by dz. And I'm going to move the negative to the right side of the equation, so we have dp dz equals negative rho g. So to put this in terms of an ideal gas, we know that rho equals mass over volume. We also know that mass can be equal to the number of moles times the molecular weight over volume. And if we look here, we can kind of do some substitution with the ideal gas law, PV equals nRT. So to get N over R, N over our volume, that's just pressure over RT. So you can substitute this in here. So we get that density equals P times the molecular weight over the gas constant R times temperature. And then we can substitute this in here. So we get dP dz equals negative pressure times molecular weight times gravity divided by gas constant R times the temperature. And this is how we can derive the basic equation of statics for an ideal gas through differentiating the volume and applying a force balance, and then substitution with the ideal gas law. Okay, so this next part we are going to derive a relationship between temperature and pressure for an adiabatic reversible process of an ideal gas. Adiabatic and reversible just simply means that there's no change in heat, there's no heat being put in or being taken out. And reversible just means that the pressure outside of the system is equal to the pressure inside of the system. So the first law of thermodynamics is that, sorry, one second, is that du, which is the differential for internal energy, equals dq minus dw. And since this is adiabatic and reversible, we know that this is 0. We know another way to describe the differential for internal energy is that du equals the specific heat of an ideal gas at a constant volume times the differential of temperature, and then the differential of work also equals pressure outside of the system times the differential of volume. So if we substitute these into the equation, we get Cv dt equals negative P dV. And if we look at the ideal gas law, we can substitute pressure. So we know that PV equals nRT, and then P equals RT over V. And we're going to say that we just have 1 mole of an ideal gas. So we can put this here, and we have Cv dt equals negative RT over V dV. And then we're going to move temperature to the left side of the equation so we can integrate. So we have Cv times dt over T equals negative R dV over V. Integrate both sides. Our parameters, we're saying that we're doing an expansion of a gas from state 1 to state 2. So we'll call this T1, T2, V1, V2. So if you do integration, we get Cv times the natural log of T2 over T1 equals negative gas constant R times the natural log of V2 over V1. And one of the properties of logarithms is that the coefficients in front can become exponentials for the terms inside. So we get natural log of T2 over T1 equals natural log of V2 over V1 raised to the power of negative R over Cv. And then if we raise both sides to the power of E, we just get T2 over T1 equals V2 over V1 raised to the negative R over Cv. We can next substitute V2 and V1 based on the ideal gas law. So again, PV equals nRT. We're going to say n is 1 still. So V equals RT over P. And then this is true for V2 and V1. So we would adjust the parameters down here to match these. So then we get T2 over T1 equals, so V2 is RT2 over P2 times the inverse of V1, so P1 over T1 times R. And this is still raised to the negative R over Cv. The gas constants cancel out, so we are left with T2 over T1 equals T2 over T1 times P1 over P2 raised to the negative R over Cv. So we notice that we have a T1 over, or T2 over T1 term here, and we also have one here. So what we want to do is multiply both sides by T2 over T1 times just a positive C, or R over CV. T2 over T1. So then we can cancel this part inside, and we are left with just pressure on the right side of the equation. So we have T2 over T1 times 1 plus R over CV equals P1 over P2 times negative R over CV. And then we're going to take this exponential right here and just simplify it to get a common denominator. So we have T2 over T1, and then it's raised to the power of CV plus R over CV, and then this is still equal to P1 over P2 raised to the negative R over CV. And then we want to raise both sides to the inverse, or the reciprocal of this, so we can just get T2 over T1 by itself. So I'll just represent that like this. So then we are left with T2 over T1 equals P1 over P2. So when you have two exponentials, you multiply them. The CV down here and up here cancels, so you're left with a negative R over CV plus R. And this equation is answer to our second part, and this describes the relationship of temperature and pressure of an ideal gas for an adiabatic reversible expansion. And then part 3, we will talk about how we can blend our equations from up here that we derived first. This one for the statics, and then we'll combine that with this one here to show another relationship. Okay, so for this final part, we're going to be combining the equation of statics for an ideal gas with this equation we derived that relates temperature and pressure for an ideal gas during an adiabatic reversible expansion. So first, we're going to look at this equation here. We're going to call T2 and P2 just T and P respectively, and we're going to use just a little substitution and call this, we're just going to call that alpha. So with that, we have T over T1 equals P1 over P raised to the power alpha. To get temperature by itself, we multiply both sides by the first temperature, and that is multiplied by this. So now we're going to substitute this equation right here, so that we have dP over dz equals negative P times molecular weight times gravity over R, and then this is multiplied by T1 times P over P1 raised to the power alpha. And you notice that we have a P here and a P here, so we can combine those to be P1 plus alpha mg divided by R T1 P1 to the alpha. So now we want to get the pressure right here on the other side of the equation, so it can be with dP, and then we'll multiply by dz, so we can eventually integrate. So we have P to the negative 1 minus alpha dP equals molecular weight G divided by R T1, and then I'm going to put this P1 out front, but it's still going to be considered constant when we integrate with respect to z. So for the parameters, we're just going to do P1 and P final, and Z1 and Z final. And remember, P1 and Z1 are our initial conditions, and Z represents the altitude. So if we integrate, we're adding 1, so the coefficient will be 1 over alpha times P to the negative alpha minus P final, minus P1 to the negative alpha. And this equals this sort of constant times the final altitude minus our starting altitude. I'm going to multiply both sides by, 1 second, I think I'm missing a negative sign. Yes. Multiply both sides by negative alpha, so we have P final to the negative alpha minus P1 to the negative alpha equals alpha times molecular weight times G divided by R T1 P1 to the negative alpha, all multiplied by the difference in altitude. So notice that we have a P1 to the negative alpha term here and a P1 to the negative alpha term here. So we can move this one to this side and combine terms. So we have 1, because that's this one that we brought over, plus alpha times molecular weight times gravity divided by R T1 times EF. So we have this equation, and then we want to raise the power to the negative 1 over alpha, so we can get these pressure terms to be to the power of 1, I suppose. So we have the final pressure equals starting pressure times 1 plus alpha molecular weight times gravity divided by R times T1 times the final altitude subtracted by the initial, all raised to the 1 over alpha power. So this here is sort of the relationship for pressure when we combine these two equations up here. So now what we want to do is we want to take this equation here and put that into this equation for P right here. So we have T equals T1 times P1 over P alpha, and we're going to put the P final here. So then this will equal T1 times, these P1s will cancel out here, so we're just left with 1 plus alpha times molecular weight times gravity over T1, multiplied by the difference in altitude, and then these powers here cancel out as well. So to make a substitution for alpha, which I will do for this equation too, is negative R over CV plus R. To confirm that that's correct, yes. So I'll expand the pressure equation so it's not in terms of alpha. Minus the r's cancel, so we have this and then here we have the difference in altitudes raised to the opposite reciprocal of alpha, so just CV plus R over R, and this ultimately is a relationship of pressure for the combination of the two equations, and then I will just do the same thing here. So we will get the final temperature equals the first temperature multiplied by 1 minus molecular weight times G over T1 times Cv plus R multiplied by the difference and the altitudes. So this is our equation for the relationship of temperature when we combine the basic equation of statics for an ideal gas with our derivation of an adiabatic reversible expansion of an ideal gas. So yeah, thank you.